Close your eyes and feel the solid ground beneath you. The floor. The foundation. The earth that holds you safe. But what if I told you that far below, deeper than the deepest roots of ancient trees, there lies something extraordinary? Something so vast and powerful that it makes ordinary volcanoes seem like tiny candles next to roaring bonfires. These are the supervolcanoes. The sleeping giants of our world. You might picture a volcano as a perfect cone-shaped mountain, like the ones in children's books. Smoke rising from a neat crater at the top. Lava flowing down tidy slopes. But supervolcanoes are different. They are not mountains at all. Instead, imagine a massive underground chamber. A hollow space so enormous that entire cities could fit inside. Picture this chamber filled not with air, but with molten rock so hot it glows like liquid starlight. This molten rock, called magma, waits patiently in the darkness. It has been waiting for thousands of years. The chamber walls are made of solid rock, thick and strong. They hold back pressures that could crush diamonds. They contain temperatures that could melt copper pennies in seconds. Yet from the surface, you would never know they are there. Above these hidden chambers, the world goes about its daily business. Grass grows. Rivers flow. Cities rise and fall. People live entire lifetimes without ever knowing that beneath their feet lies one of the most powerful forces on Earth. The word super means more than ordinary. Much more. When scientists first discovered these giants, they needed a new way to measure volcanic power. Regular volcanoes rate on a scale from 1 to 8. Most eruptions you hear about in the news rate a 2 or 3. Mount Vesuvius, which buried the ancient city of Pompeii, was only a 5. But supervolcanoes? They break the scale. They are 8s. The difference between a regular volcano and a supervolcano is like the difference between a firecracker and a thunderstorm. When a supervolcano awakens, it does not simply erupt. It empties. The entire underground chamber collapses inward, creating a bowl-shaped depression called a caldera. This collapse happens so suddenly that the ground above simply disappears. Where there once was land, there is now a crater dozens of miles across. But here is what makes this story beautiful rather than frightening. These events happen so rarely that they are measured not in human lifetimes, but in geological time. The last supervolcanic eruption occurred 74,000 years ago, long before your great-great-grandmother's great-great-grandmother was even born. Think of it this way. If the Earth's entire history was compressed into a single year, supervolcanic eruptions would happen about as often as leap years. They are rare. Precious, almost. Like shooting stars in slow motion. Tonight, as you lie in your bed, there are only a handful of these sleeping giants around the world. Yellowstone in the United States. Toba in Indonesia. Taupo in New Zealand. Each one rests quietly, their massive chambers slowly filling and emptying like the lungs of some ancient, dreaming creature. The magma moves so slowly that you could watch it for your entire lifetime and never see it change position. It flows like thick honey on a cold morning. It rises a few inches per year. Sometimes it sinks back down. The giants breathe, but their breaths last centuries. Scientists have learned to read the signs of these slow breaths. They place sensitive instruments on the ground above the chambers. These instruments can feel the earth lift up by less than the thickness of a piece of paper. They can detect heat rising through solid rock. They can taste gases that seep up from the deep chambers, each molecule carrying news from the world below. This is where our journey begins. With the understanding that beneath our feet lies a world as alien as any distant planet, yet as much a part of Earth as the air we breathe. A world where time moves differently. Where pressure and heat create wonders that exist nowhere else. The sleeping giants have been dreaming their slow dreams since before humans learned to speak. They will continue dreaming long after our great-grandchildren's great-grandchildren have become dust. There is something deeply comforting about this vast scale of time. It reminds us that some things in the universe are larger than our daily worries. Older than our fears. As you settle deeper into sleep tonight, know that you are part of this ancient story. Your body is made of elements that were once deep in the Earth's core. The calcium in your bones, the iron in your blood, all of it was once part of the same slow, patient dance that feeds the sleeping giants. You are connected to these deep chambers not by fear, but by the simple fact that you are both made of earth. You both follow rhythms. Yours is the rhythm of heartbeat and breath. Theirs is the rhythm of rising magma and cooling rock. But how do scientists listen to these sleeping giants? How do they hear whispers from chambers buried miles beneath solid stone? Place your hand gently on your chest. Feel that steady rhythm. Lub-dub. Lub-dub. Your heart beats about 70 times every minute. 4,000 times every hour. Over 2 million times each month. This is the rhythm of your life. Fast, urgent, keeping pace with your thoughts and dreams. But far beneath you, the earth has its own heartbeat. So slow you could never feel it. So deep you could never hear it. Yet it has been beating since long before the first human heart ever took its first beat. This is the heartbeat of stone and magma. In the darkness below, molten rock moves like thick, glowing honey. It does not rush or hurry. It follows currents that take centuries to complete a single cycle. Imagine a river so patient that a single drop takes 1,000 years to travel from its source to its mouth. The magma rises from depths where pressure could crush mountains. It comes from places where rock becomes liquid, where diamonds melt like ice cream on a summer day. As it rises, it cools. As it cools, it becomes denser. As it becomes denser, it begins to sink back down. This creates what scientists call a convection cell. Think of a pot of soup simmering on a stove. Hot soup rises to the surface, cools, then sinks back down to be heated again. The Earth's magma chambers work the same way, but their soup pot is miles deep and their simmer lasts for millennia. Scientists have placed instruments called seismometers around the world. These are like electronic stethoscopes for the Earth. They listen to vibrations so faint that they would be impossible for human ears to detect. When you walk across a wooden floor, the boards creak and bend slightly under your weight. When magma moves deep underground, it does the same thing to solid rock. The rock bends. It stretches. Sometimes it cracks with sounds too low for you to hear. These sounds travel up through miles of stone. They move at the speed of earthquake waves, racing through the Earth's crust like ripples through water. When they reach the surface, the seismometers are waiting. Each vibration tells a story. Fast, sharp vibrations mean rock is breaking suddenly. Slow, rolling vibrations mean something heavy is moving gradually. The scientists read these vibrations like sheet music, hearing melodies written in stone. But the Earth's heartbeat has more than just sound. It has temperature. Deep magma chambers glow with heat that could melt copper. This heat does not stay trapped forever. It seeps upward through cracks and spaces in the rock above. Like warmth from a campfire reaching your hands, thermal energy rises toward the surface. Scientists measure this heat with instruments that can detect temperature changes smaller than you could feel with your skin. They create maps of warmth, painting pictures of the hot chambers hidden below. Where the maps show the most heat, they know magma is closest to the surface. Where the maps show cooler temperatures, they know the magma has moved deeper or cooled. Like tracking a fever in the Earth's body, they watch these thermal patterns change over time. The patterns reveal the Earth's slow breathing. In some years, more heat reaches the surface. The underground chambers are fuller, more active. In other years, less heat makes the journey upward. The chambers rest, like a sleeping animal with slower breathing. This thermal breathing happens in cycles. Sometimes the cycles last decades. Sometimes they last centuries. Scientists have learned to read these cycles like seasons, understanding that the Earth has its own version of spring and winter, activity and rest. The combination of seismic vibrations and thermal patterns creates what scientists call the Earth's vital signs. Just as doctors listen to your heart and check your temperature, scientists monitor the planet's pulse and fever. But there is something beautiful about this monitoring. Unlike a patient who might be sick, the Earth's vital signs show a system that is working perfectly. The heartbeat of stone and magma is not a sign of trouble. It is a sign of life. The same forces that created the mountains you see today. The same energy that will create new mountains tomorrow. The same slow, patient power that has been shaping continents since the Earth was young. When you feel overwhelmed by the speed of your daily life, remember the Earth's heartbeat. Remember that some of the most important work in the universe happens slowly. Remember that patience is not just a human virtue. It is written into the very bones of the planet. The magma chambers beneath supervolcanoes are not rushing toward eruption. They are following rhythms older than any human civilization. Their heartbeat is steady, predictable, comforting in its ancient reliability. Tonight, as your own heartbeat slows toward sleep, you can take comfort in knowing that the Earth's heart beats on. Deep below, molten rock continues its patient dance. Heat continues its slow journey toward the surface. Seismometers continue their faithful listening. But the Earth's heartbeat is only part of the story. Above the magma chambers, something else is happening. Something so subtle that only the most sensitive instruments can detect it. The very ground beneath your feet is moving, breathing like a living thing. Watch your chest as you breathe. See how it rises slowly, then falls. Up and down, in a rhythm so natural you never think about it. Each breath lifts your ribs, expands your lungs, then gently releases. The Earth breathes too. But its breaths are so slow, so vast, that you could live your entire life and never notice a single inhale. Above the sleeping magma chambers, the ground itself moves up and down. Not quickly, like an earthquake. Not violently, like a landslide. But slowly, gently, like the chest of some enormous sleeping creature. This breathing happens because deep below, the magma chambers fill and empty like slow, underground lungs. When more molten rock flows into a chamber, the pressure increases. The weight of all that liquid stone pushes upward against the solid rock above. Gradually, over years and decades, the ground rises. Sometimes it rises only inches. Sometimes it rises several feet. But it rises so slowly that the trees growing on the surface never notice. The grass keeps growing. The streams keep flowing. Only the most sensitive instruments can detect this patient lifting. Scientists call this ground deformation. It sounds like a harsh word, but it describes something beautiful. The Earth reshaping itself with the gentleness of a sleeping breath. In Yellowstone National Park, there is a place called the Sour Creek Dome. Between 1923 and 1984, this area rose more than 3 feet. That might not sound like much, but imagine an area the size of a city slowly lifting up, like a giant balloon inflating underneath the ground. The lifting was so gradual that visitors to the park never felt it happening. They walked the same trails, saw the same geysers, never knowing that the land itself was rising beneath their feet. Then, in the 1990s, something changed. The ground began to sink. Not collapse, not crash, but gently subside. Like an exhale after a long, deep breath. The magma chamber below had shifted, and the surface followed its lead. This is how scientists first learned to read the Earth's breathing patterns. They placed precise measuring tools across the landscape above known supervolcanoes. These tools can detect changes smaller than the thickness of a fingernail. Some of these instruments use satellites far above the Earth. The satellites send radio signals down to receivers on the ground. By measuring how long the signals take to travel, scientists can calculate the exact height of each receiver. If the ground rises even a tiny amount, the signal takes a little less time to arrive. If the ground sinks, the signal takes a little longer. Other instruments work like electronic levels. They sit on the ground and feel the slightest tilt. When one side of a magma chamber fills more than the other, the ground above tilts like a seesaw. The instruments detect this tilt, even when it is so small that a marble placed on the ground would barely know which way to roll. There are also instruments that work like underground compasses. They measure how the Earth's magnetic field changes when hot magma moves below. Hot rock affects magnetism differently than cool rock. As magma chambers shift and change, they create magnetic shadows that these instruments can read. All of these measurements create what scientists call a deformation map. It shows which areas are rising, which are falling, and which are staying steady. The map looks like a topographic chart of an invisible landscape, showing mountains and valleys made of pressure and time. Reading these maps requires patience and years of observation. A single measurement means nothing. But when scientists collect thousands of measurements over decades, patterns emerge. They can see the Earth's breathing rhythm. Some supervolcanoes breathe in quick cycles. Their ground rises and falls over decades. Others have slower rhythms, with breathing cycles that last centuries. Each supervolcano has its own pattern, like a fingerprint made of stone and time. The most important discovery is that this breathing is normal. Healthy, even. It shows that the magma chambers below are following natural cycles of filling and cooling. The rising and falling is not a sign that an eruption is coming soon. It is a sign that the system is working exactly as it should. Think of it like the tides. Twice each day, the ocean rises and falls along every coastline. This rhythm has continued for millions of years. It is not a sign of danger. It is a sign of balance, of natural forces working in harmony. The Earth's breathing works the same way. The rising and falling of land above magma chambers is part of a natural rhythm that has continued for thousands of years. Scientists find comfort in this predictability. Even the most powerful forces on Earth follow patterns that can be understood and measured. But ground deformation tells scientists something else important. It shows them the shape and size of the magma chambers below. By watching how the surface rises and falls, they can create maps of the hidden chambers. They can see which parts are deepest, which parts are closest to the surface, and how the chambers connect to each other. This is like watching the shadow of a fish moving beneath the surface of a calm lake. You cannot see the fish directly, but its shadow tells you exactly where it is and how it is moving. Tonight, as you lie still and feel your own gentle breathing, remember that the Earth beneath you breathes too. Somewhere below, magma chambers are slowly filling and emptying. Somewhere above, satellites are measuring tiny changes in the ground. Scientists are reading the Earth's vital signs, finding reassurance in patterns older than human memory. The breathing of the Earth connects you to something vast and ancient. Your quick, light breaths and the planet's slow, heavy breaths are part of the same story. Both are signs of life, of energy moving through systems that have learned to sustain themselves over time. But breathing is not the only way the sleeping giants communicate with the surface. Deep in their chambers, heat is constantly rising, creating its own language of warmth and steam. Feel the warmth of your own body. Even now, as you rest quietly, heat radiates from your skin into the cooler air around you. This invisible energy flows outward in gentle waves, warming everything it touches. The Earth works the same way. Deep in its molten core, temperatures reach thousands of degrees. This heat cannot stay trapped forever. Like warmth from your body, it must find a way to escape. So it begins a journey upward. Through miles of solid rock. Through layers of stone that have never seen sunlight. The heat moves slowly, patiently, following paths of least resistance through tiny cracks and pores in the rock. This journey takes time. Not minutes or hours, but centuries. A single unit of heat energy that begins its journey in the Earth's core today might not reach the surface until your great-grandchildren are old and grey. But when that heat finally arrives at the surface, it creates magic. In places like Yellowstone, Iceland, and New Zealand, this deep heat meets the world above. It warms underground water until the water becomes steam. It creates hot springs that bubble and gurgle with the voice of the Earth itself. It powers geysers that shoot columns of superheated water high into the air. These thermal features are like letters in an alphabet written by the planet. Each hot spring, each geyser, each warm patch of ground is a word in a language that scientists have learned to read. The temperature of a hot spring tells them how deep the heat source lies. Very hot springs, those that could cook an egg in seconds, usually sit directly above active magma chambers. Cooler springs might be heated by rock that was warmed by magma long ago, but has since moved away. The chemistry of the hot water tells them what kinds of rock the heat has traveled through. Different minerals dissolve into the water as it heats up underground. When scientists test the water, they can tell whether it has passed through limestone, granite, or volcanic rock. The timing of geysers tells them about underground plumbing. Some geysers erupt every few minutes. Others wait hours between eruptions. A few rare geysers erupt only once every few years. Each pattern reveals something about the shape and size of the underground chambers where the heated water collects. Scientists use special cameras that can see heat the way your eyes see light. These thermal cameras paint pictures of the landscape in colors of temperature. Hot areas glow bright red and yellow. Cool areas appear in blues and purples. The result looks like a rainbow painted across the ground. When they point these cameras at areas above supervolcanoes, they see patterns invisible to normal sight. Long lines of warmth that mark underground fractures where heat escapes. Circular patches of heat that show where magma chambers lie closest to the surface. Cool spots where thick layers of rock insulate the surface from the heat below. These thermal maps change over time. In some years, certain areas grow warmer. More heat is reaching the surface, suggesting increased activity in the magma chambers below. In other years, the same areas cool down, indicating that the chambers have shifted or that the heat flow has decreased. But the most beautiful part of this thermal language is how gentle it is. The heat that powers the most dramatic geysers is the same heat that creates the most peaceful hot springs. The energy that could melt rock deep underground becomes, at the surface, a warm bath that could soothe tired muscles. This transformation happens because heat, like everything else in nature, seeks balance. The extreme temperatures of the deep earth moderate as they rise toward the surface. They become life-giving rather than destructive. They create oases of warmth in cold mountain valleys. They provide refuge for plants and animals during harsh winters. Indigenous peoples around the world have always known about these thermal gifts. They built settlements near hot springs, understanding that the earth was offering them warmth and comfort. They developed ceremonies and stories around geysers, recognizing that these eruptions were the earth speaking in its own voice. Modern science has confirmed what these ancient peoples always knew: thermal features are windows into the Earth's heart. They show us the planet not as a cold, dead rock, but as a living system with its own circulation, its own way of regulating temperature and pressure. Tonight, as you feel your own body heat warming the blankets around you, remember that you are part of this same thermal story. The warmth you generate comes from the same basic processes that heat the Earth's core. Chemical reactions releasing energy. Movement creating friction. Life sustaining itself through the careful management of temperature. You and the Earth are both warm-blooded in your own ways. Both of you work constantly to maintain the right temperature for the processes that keep you alive. Both of you radiate excess heat into your surroundings, creating comfort for others. The thermal language of supervolcanoes continues to whisper its ancient messages day and night. Steam rises from hot springs under starlight. Geysers mark time with their patient rhythms. Underground, heat continues its slow journey toward the surface. But heat is not the only message traveling upward from the deep chambers. There are other whispers, carried not by warmth, but by the very atoms and molecules that make up rock itself. Hold a piece of quartz up to the light. See how it sparkles, how its surface catches and bends the rays into tiny rainbows. What you are seeing is not just a pretty rock. You are looking at one of nature's most perfect arrangements of atoms. Inside that crystal, millions of silicon and oxygen atoms are arranged in precise, repeating patterns. Like dancers frozen in perfect formation, each atom knows exactly where it belongs. This arrangement is called a crystal lattice, and it is one of the most organized structures in the natural world. But here is what makes crystals magical: they remember everything that has ever happened to them. When pressure increases around a crystal, its atoms squeeze closer together. When temperature rises, the atoms vibrate more quickly. When chemical conditions change, some atoms might leave their positions and new ones might take their place. Each of these changes leaves a permanent mark in the crystal's structure. Scientists have learned to read these marks like pages in a book. They can tell when a crystal formed, what conditions it experienced, and how those conditions changed over time. The crystal becomes a witness to events that happened millions of years ago. In the rocks around supervolcanoes, crystals tell stories of immense heat and pressure. They speak of magma chambers filling and cooling. They record the slow dance of molten rock as it rises toward the surface, then sinks back down into the depths. Some crystals form only under very specific conditions. Certain types of quartz can only grow when temperatures reach exactly the right level. Other crystals require precise amounts of pressure to form their perfect structures. When scientists find these crystals in rocks, they know exactly what conditions existed when the crystals were born. But crystals do more than just record the past. They also reveal changes happening in the present. As magma chambers deep below shift and change, the pressure and temperature around existing crystals changes too. The crystals respond by adjusting their internal structure. Atoms move to new positions. Chemical bonds stretch or compress. The crystal lattice adapts to its new environment. These changes are incredibly small. Individual atoms moving distances smaller than anything you could see, even with the most powerful microscope. But scientists have instruments sensitive enough to detect these tiny movements. They use a technique called X-ray crystallography. X-rays are beams of energy that can pass through solid rock and interact with crystal structures. When X-rays hit a crystal lattice, they bounce off the atoms in specific patterns. By studying these patterns, scientists can see the exact arrangement of atoms inside the crystal. When they compare X-ray patterns from crystals collected at different times, they can see how the atomic arrangements have changed. A crystal that was perfectly organized last year might show slight distortions this year. These distortions tell scientists that conditions deep below are changing. Another technique uses polarized light, which vibrates in only one direction. When this special light passes through crystals, it behaves differently depending on how the atoms are arranged. Crystals under stress bend the light in characteristic ways. By studying how light behaves as it passes through rock samples, scientists can detect stress patterns that are invisible to the naked eye. The most sensitive crystals are those that contain trace amounts of radioactive elements. These elements decay at known rates, releasing tiny amounts of energy as they transform into other elements. This process is like a natural clock, ticking away inside the crystal structure. When scientists measure the ratios of parent and daughter elements in these crystals, they can calculate how long the decay process has been running. This tells them the age of the crystal. More importantly, if the decay rate appears to have changed recently, it suggests that the crystal has experienced new stresses or temperature changes. The crystals found in volcanic rocks often contain tiny bubbles of liquid or gas trapped inside. These bubbles are samples of the conditions that existed when the crystal formed. They contain water, carbon dioxide, and other chemicals that were present in the magma chamber millions of years ago. By analyzing these trapped bubbles, scientists can reconstruct the history of magma chambers. They can tell how hot the magma was, how much gas it contained, and what minerals were dissolved in it. They can even detect changes in the magma's composition over time. This information helps scientists understand how magma chambers evolve. They learn which chambers are growing more active and which are cooling down. They discover how gases build up and are released. They track the slow processes that might, over thousands of years, lead to volcanic activity. But perhaps the most beautiful aspect of crystal science is how it reveals the connection between the very small and the very large. Atoms rearranging themselves in response to changes in pressure. These atomic movements reflecting shifts in massive magma chambers miles below the surface. The smallest possible changes recording the largest possible forces. The crystals in volcanic rocks are like libraries where the Earth stores its memories. Each crystal is a book written in the language of atomic structure. Each change in the crystal lattice is a new page added to the story. Scientists who study these crystal libraries often describe their work as listening to whispers. The crystals speak so softly that you need the most sensitive instruments to hear them. But when you learn their language, they tell you stories of incredible beauty and power. Tonight, as you rest, crystals all around the world are continuing to record the Earth's ongoing story. In laboratories, scientists are reading the latest chapters written in stone. They are discovering how the sleeping giants deep below are stirring, stretching, adjusting their positions in ways so subtle that only crystals can detect them. The crystal lattices hold their secrets patiently, waiting for scientists to ask the right questions. They have been keeping these records for millions of years, and they will continue keeping them for millions more. But crystals are not the only record keepers in the Earth's library. High above the surface, other observers are watching and recording, gathering information that crystals alone cannot provide. Take a slow, deep breath. Feel the air fill your lungs, then slowly release it. That breath you just exhaled carries traces of everything you have eaten today, everywhere you have been, even the emotions you have felt. Each molecule in your breath tells a story. Oxygen from the plants around you. Carbon dioxide from the energy your cells have burned. Tiny amounts of other gases that reveal the unique chemistry of your body. The Earth breathes too. And its breath carries stories from places no human has ever been. Deep in the magma chambers beneath supervolcanoes, gases bubble up through molten rock like champagne rising in a glass. These gases are born from conditions of incredible heat and pressure. They carry the chemical signature of the Earth's deepest dreams. When these gases finally reach the surface, they seep up through cracks in the ground. Sometimes they emerge from hot springs, making the water bubble and fizz. Sometimes they form invisible clouds that drift across the landscape. Sometimes they collect in caves and underground spaces, creating pockets of ancient air. Scientists have learned to capture these gases and read their stories. Each type of gas molecule is like a letter in an alphabet. When they decode the combinations, they can understand messages written in the language of deep Earth chemistry. Water vapor is the most common gas that rises from magma chambers. But this is not ordinary water that has fallen as rain or flowed in rivers. This is water that has been locked in rock for millions of years. Water that has been heated and pressurized until it becomes something almost magical. When scientists analyze this ancient water vapor, they can tell how deep it originated. Water from shallow depths has one chemical signature. Water from the deepest parts of magma chambers has another. By comparing these signatures, they can map the internal structure of underground chambers they have never seen. Carbon dioxide tells different stories. Some of it comes from limestone and other rocks that dissolve when heated by magma. This carbon dioxide carries traces of ancient sea floors and fossilized life forms. Other carbon dioxide comes directly from the molten rock itself, carrying messages from the Earth's mantle. The ratio between these different types of carbon dioxide tells scientists how active the magma chamber is. More rock-derived carbon dioxide suggests increased melting and chemical activity. More limestone-derived carbon dioxide might indicate that the magma is interacting with sedimentary rocks above. Sulfur gases create some of the most distinctive signatures. These gases smell like rotten eggs, but to scientists they smell like information. Different sulfur compounds form under different conditions of temperature and acidity. By identifying which sulfur gases are present, scientists can determine the exact chemical environment inside the magma chamber. Helium might seem like a party balloon gas, but in volcanic contexts it carries profound messages. There are two main types of helium on Earth. One type comes from the decay of radioactive elements in the crust. The other type has been trapped in the Earth's mantle since the planet formed billions of years ago. When scientists find high concentrations of mantle helium in volcanic gases, they know the magma is coming from very deep sources. This ancient helium is like a messenger from the Earth's birth, carrying information about processes that began when the solar system was young. The most sensitive instruments can detect gas concentrations measured in parts per billion. That is like finding a single drop of food coloring in an Olympic-sized swimming pool. These tiny concentrations reveal changes happening deep underground that would be impossible to detect any other way. Scientists collect these gas samples using special techniques. Sometimes they lower collection tubes into hot springs and fumaroles. Sometimes they use helicopter-mounted equipment to sample gases from volcanic vents. Sometimes they even send robotic collectors into areas too dangerous for humans to enter. The timing of gas emissions tells its own story. Some gases are released constantly, like the Earth breathing at a steady rate. Others come in pulses, suggesting that pressure is building and releasing in cycles deep below. A few rare gases appear only during periods of increased activity, serving as early warning signals. But the most beautiful aspect of volcanic gas chemistry is how it reveals the Earth as a living, breathing system. The same processes that create the air you breathe also create these volcanic gases. The same chemical cycles that sustain life on the surface also operate in the planet's deepest chambers. The gases rising from supervolcanoes today were once part of ancient oceans, buried forests, and prehistoric atmospheres. They have been recycled through the Earth system countless times, sometimes spending millions of years locked in rock, sometimes floating free in the atmosphere. When you breathe, you are participating in this same grand recycling system. Some of the oxygen in your lungs might have once bubbled up from a volcanic hot spring. Some of the carbon dioxide you exhale might eventually find its way into a magma chamber, beginning another journey through deep time. Tonight, as you settle into sleep, volcanic gases continue their patient rise from the depths. They carry their chemical messages upward, telling stories of heat and pressure, of rock and time, of the slow processes that keep our planet alive and changing. Scientists around the world are collecting these gaseous messengers, translating their chemical poetry into understanding. Each sample adds another line to the great book of Earth's ongoing story. But these rising gases are not the only messengers traveling between the deep chambers and the surface world. Far above, mechanical eyes in orbit are watching, measuring changes too subtle for any ground-based instrument to detect. Look up at the night sky. Among those points of light, some are not stars at all. They are satellites, mechanical guardians that circle our planet in silent orbits. While you sleep tonight, they continue their patient watch, measuring changes in the Earth that happen too slowly for any human to notice. These satellites are equipped with instruments more sensitive than any human sense. They can detect movement smaller than the thickness of a coin. They can measure heat differences so slight that your skin could never feel them. They can see through clouds and darkness, watching the Earth's surface with eyes that never blink. Above the sleeping giants of supervolcanoes, these orbital watchers perform a dance of precision. They send radio waves down to the Earth's surface, timing how long the signals take to bounce back. When the ground rises even a tiny amount, the signal returns a fraction of a second sooner. When the ground sinks, the signal takes a little longer to complete its journey. This technique, called radar interferometry, creates maps of ground movement that look like topographic charts painted in rainbow colors. Each color represents a different amount of vertical movement. Deep blues show areas that are sinking. Bright reds show areas that are rising. The patterns that emerge tell stories of underground forces invisible from the ground. From their high orbits, satellites can see the entire breathing pattern of a supervolcano at once. They can watch how different parts of the ground rise and fall at different rates. They can track how these patterns change from season to season, year to year, decade to decade. In Yellowstone, satellites have watched the ground rise and fall in slow cycles that last for years. The Sour Creek Dome, which we visited in an earlier chapter, shows up clearly in satellite data as a gentle bulge that grows and shrinks like a slow-motion bubble beneath the Earth's surface. Other satellites specialize in measuring heat. They use infrared sensors that can detect temperature differences of less than 1 degree. From space, they create thermal maps that show how heat flows across the landscape above supervolcanoes. These heat maps reveal thermal patterns that would be impossible to see from the ground. Long lines of warmth that mark underground fractures. Circular patches of heat that show where magma chambers are closest to the surface. Cool zones where thick layers of rock insulate the surface from the heat below. The thermal satellites also track how these heat patterns change with the seasons. In winter, the contrast between hot springs and the surrounding landscape becomes more dramatic. In summer, solar heating can mask some of the subtle thermal signatures of underground activity. Some satellites carry instruments that can measure the Earth's gravity field with extraordinary precision. Gravity changes when mass moves underground. When magma flows into a chamber, the increased mass creates a slight increase in gravitational pull. When magma drains away, gravity decreases. These gravity measurements are so sensitive that they can detect changes caused by underground water levels, by the growth and melting of ice sheets, even by the movement of air masses in the atmosphere. Separating the signals caused by magma movement from all these other effects requires sophisticated mathematical techniques. But perhaps the most remarkable capability of modern satellites is their ability to work together. A constellation of satellites can observe the same area from different angles and at different times. By combining their measurements, scientists can create three-dimensional movies of how the Earth's surface moves over time. These orbital movies reveal the Earth as a dynamic, living planet. Continents rise and fall with the tides. Mountain ranges sway slightly in response to atmospheric pressure changes. Ice sheets grow and shrink with the seasons. And underneath it all, the slow breathing of magma chambers creates patterns of movement that persist for decades. The satellites never rest. As the Earth rotates beneath them, they continuously scan the surface, building up massive databases of measurements. Each pass over a supervolcano adds new data to the growing record of how these systems behave over time. Ground-based instruments can tell scientists what is happening at specific points. Satellites tell them what is happening across entire regions. Together, these observations create a complete picture of how supervolcanoes breathe, shift, and change. The data from satellites often reveals surprises. Areas that seem completely stable from the ground might show subtle movement patterns when viewed from space. Regions that appear to be rising might actually be tilting. What looks like random variation might actually follow predictable cycles. But satellites do more than just collect data. They also provide a new perspective on our place in the universe. From their orbital viewpoint, national boundaries disappear. Political divisions become meaningless. The Earth appears as what it truly is, a single, integrated system where everything is connected to everything else. The volcanic systems that satellites monitor are part of this larger planetary system. The same forces that power supervolcanoes also drive the movement of continents, the creation of mountain ranges, and the circulation of the oceans. From space, these connections become visible in ways they never could from the ground. Tonight, as you drift towards sleep, dozens of satellites continue their silent orbits overhead. Their sensors are recording data that will help scientists understand not just what supervolcanoes are doing now, but what they might do in the future. The orbital perspective reminds us that the Earth's processes operate on scales both vast and intimate. The same planet that cradles you as you sleep also harbors forces powerful enough to reshape continents. The same gentle movements that satellites detect with such precision are connected to the deep rhythms that have been shaping our world for billions of years. But the satellites are not the only ones keeping records of these ancient rhythms. Deep in lake beds and ice sheets, other archives are being written, preserving the memory of past volcanic events in layers that span millennia. Imagine opening a book where each page represents a single year, stretching back through time. The first few pages might tell the story of your lifetime. Turn deeper, and you find pages describing the lives of your grandparents. Keep turning, and you discover stories from centuries ago, then millennia, then hundreds of thousands of years into the past. Such books exist in nature. They are written not in words, but in layers of mud, dust, and ice. Each layer is a page that records what happened during a specific time period. And some of these natural books contain chapters about supervolcanic eruptions that occurred long before humans existed. At the bottom of quiet lakes, sediment settles like snow falling through water. Each year, new material drifts down to join the layers below. Pollen from nearby trees. Dust carried by the wind. Microscopic plants and animals that lived and died in the water above. Most years, these layers are thin and unremarkable. They speak of ordinary seasons, normal weather, the peaceful passage of time. But some layers are different. Some layers tell stories of extraordinary events. When a supervolcano erupts, it sends ash and dust high into the atmosphere. This material can travel thousands of miles before settling to the ground. Some of it lands in lakes, creating distinctive layers that mark the exact time of the eruption. Scientists who study these lake bed records are like detectives reading ancient crime scenes. They lower hollow tubes deep into the lake bottom sediments, pulling up cores that contain hundreds of thousands of years of history. When they slice these cores open, they reveal the layers like pages in a book. Most volcanic ash layers are surprisingly thin. An eruption that darkened skies across an entire continent might leave a layer only a few inches thick at the bottom of a distant lake. But that thin layer contains a wealth of information. The chemical composition of the ash tells scientists which volcano it came from. Each volcano produces ash with a unique chemical fingerprint, like a signature written in stone. By analyzing this fingerprint, scientists can match ash layers found in different lakes, proving they came from the same eruption. The size of the ash particles tells them how powerful the eruption was. Larger particles fall closer to the volcano. Smaller particles can travel farther. By measuring the size distribution of particles in different ash layers, scientists can estimate the force of ancient eruptions. The thickness of ash layers at different distances from a volcano tells them how much material the eruption produced. A thick ash layer found hundreds of miles away suggests an eruption of enormous magnitude. A thin layer might indicate a smaller event, or an eruption whose main force was directed in a different direction. But lake sediments preserve more than just volcanic ash. They also record how ecosystems recovered after major eruptions. In the layers immediately above an ash deposit, scientists often find changes in the types of pollen present. Some plant species disappear from the record, killed by the ash fall or climate changes caused by the eruption. Other species become more common, taking advantage of newly cleared land. These recovery patterns teach scientists about the resilience of life. Even after the most devastating supervolcanic eruptions, ecosystems gradually rebuild themselves. New forests grow. Animal populations recover. Within centuries or millennia, the natural world returns to something resembling its former state. Ice cores from Greenland and Antarctica provide another type of natural archive. As snow falls and compresses into ice, it traps samples of the ancient atmosphere. Air bubbles in the ice contain the actual gases that existed in the atmosphere thousands of years ago. When a supervolcanic eruption sends sulfur compounds into the atmosphere, these chemicals show up clearly in ice core records. The sulfur causes the ice to become more acidic. Scientists can measure this acidity and use it to identify volcanic events, even when they have no other record of the eruption. Ice cores also reveal how volcanic eruptions affected global climate. Large eruptions inject particles into the upper atmosphere that can block sunlight for years. This cooling effect shows up in ice cores as changes in the chemistry of annual ice layers. The Toba eruption, which occurred about 74,000 years ago, left clear signatures in both lake sediments and ice cores around the world. This supervolcanic event was so massive that it may have triggered a volcanic winter lasting several years. Yet the geological records also show that life survived and recovered. Reading these natural archives requires patience and careful attention to detail. Scientists must account for how sediments can be disturbed by earthquakes or landslides. They must understand how different types of lakes preserve different kinds of information. They must calibrate their methods using eruptions that occurred in recorded history. But the effort is worthwhile, because these natural libraries contain information that exists nowhere else. They tell scientists how often supervolcanic eruptions occur, how powerful they tend to be, and what their effects are on climate and ecosystems. Perhaps most importantly, these records reveal that supervolcanic eruptions follow patterns. They are not random catastrophes, but part of natural cycles that have been operating for millions of years. Understanding these cycles helps scientists predict when future eruptions might occur. The sediment layers also show that recovery from volcanic events is always possible. Life finds ways to adapt and continue. Forests regrow. Lakes refill with diverse communities of plants and animals. The Earth systems have a remarkable ability to heal from even the most dramatic disturbances. Tonight, as you rest, sediments are settling quietly in lakes around the world. Each grain of dust, each piece of pollen, each microscopic organism is contributing to the ongoing record that future scientists will read. The natural libraries are still being written, one thin layer at a time. In ice sheets, snow continues to fall and compress, trapping samples of today's atmosphere for scientists who will live centuries from now. The memory keepers work without pause, preserving information that spans vastly more time than any human memory could hold. These patient archivists in lake beds and ice sheets are not the only ones keeping watch over supervolcanic systems. Around the world, networks of sensitive instruments listen constantly to the Earth's whispers, creating a global conversation about what stirs in the deep places. Press your ear against the ground. Feel the cool Earth against your skin. Listen carefully to what the solid world might tell you. You might hear nothing but silence. But if you had the right equipment, you would discover that the Earth never stops whispering. Around the world, thousands of sensitive instruments rest their mechanical ears against the ground, listening to vibrations so faint that they measure less than the width of an atom. These are seismometers, and they form a global network of patient listeners that never sleep. Each seismometer is like a sophisticated stethoscope for the planet. It can detect the footsteps of a single person walking a mile away. It can feel the vibrations of ocean waves crashing against distant shores. It can sense the rumble of trucks on highways hundreds of miles from its location. But most importantly, these instruments can hear the deep songs that rise from magma chambers far below the surface. When molten rock moves in underground chambers, it creates vibrations that travel through solid stone faster than sound travels through air. These seismic waves ripple outward from their source, carrying information about what caused them. By the time they reach the surface, they have become whispers that only the most sensitive instruments can detect. A single seismometer can tell scientists that something moved deep underground. But it cannot tell them where the movement occurred or what caused it. For that, scientists need multiple listeners working together. When the same seismic wave reaches several different seismometers, each instrument records the arrival time. Waves travel at known speeds through different types of rock. By comparing the arrival times at different stations, scientists can calculate exactly where the wave began its journey. This process is like listening to thunder and counting the seconds before you hear the rumble. The difference tells you how far away the lightning struck. But with seismic waves, scientists can use measurements from many locations to pinpoint the source with incredible precision. The global seismometer network operates like a vast, intelligent organism. When one instrument detects an unusual vibration, it automatically shares that information with monitoring centers around the world. Within minutes, scientists can determine whether the vibration came from an earthquake, a volcanic event, or even human activity like mining or construction. Near supervolcanoes, seismometer networks become especially dense. In Yellowstone, more than 30 seismometers listen continuously to vibrations from the sleeping giant below. They can detect earthquake swarms that consist of hundreds of tiny tremors, each one too small to be felt by humans but collectively revealing changes in the magma chamber. These earthquake swarms often follow patterns that tell stories about underground processes. Sometimes the earthquakes cluster in specific areas, suggesting that magma is moving into new regions of the chamber. Sometimes they occur at regular intervals, indicating that pressure is building and releasing in predictable cycles. The seismometers also detect a special type of vibration called harmonic tremor. This is not the sharp, sudden shake of a typical earthquake. Instead, it sounds like a low, continuous hum that can last for hours or days. Scientists think harmonic tremor is created by magma and gases moving through underground channels, like the sound of water flowing through pipes. When harmonic tremor appears in seismometer records, it often means that magma is actively moving somewhere in the underground system. The frequency and intensity of the tremor can tell scientists how fast the magma is moving and whether it is rising toward the surface or circulating within the chamber. Modern seismometer networks use advanced communication systems to share data instantly. When a seismometer in Alaska detects a vibration, scientists in California can see the data within seconds. This real-time sharing allows researchers to track seismic events as they unfold, sometimes even predicting where the next vibrations will occur. The networks also include different types of listening instruments. Some seismometers specialize in detecting high-frequency vibrations that travel short distances. Others focus on low-frequency waves that can circle the entire planet. Still others are designed to measure the ground's movement in 3 dimensions, tracking up and down motion as well as side-to-side movement. Together, these different types of listeners create a complete picture of how vibrations move through the Earth. They can distinguish between the sharp crack of breaking rock, the slow rumble of sliding sediments, and the continuous whisper of flowing magma. The data from seismometer networks becomes part of a global conversation about the Earth's internal activities. Scientists in different countries share information about seismic patterns they observe. They compare notes about how different volcanic systems behave. They work together to understand phenomena that cross international boundaries. This collaboration reveals that the Earth's volcanic systems are interconnected in ways that no single country could discover alone. Seismic waves from a major earthquake in one part of the world can trigger small tremors in volcanic areas thousands of miles away. The planet responds to stress as an integrated whole, not as isolated regions. The seismometer networks also serve as early warning systems for communities near active volcanoes. When unusual seismic patterns suggest increasing volcanic activity, scientists can alert local authorities and residents. These warnings have saved thousands of lives by giving people time to evacuate before dangerous eruptions occur. But perhaps the most beautiful aspect of the global seismometer network is how it demonstrates human cooperation in understanding our shared planet. Scientists from different cultures, speaking different languages, work together to listen to the Earth's deepest voices. Tonight, as you settle into quiet rest, thousands of seismometers around the world continue their patient listening. They detect vibrations from ocean storms, from shifting ice sheets, from the slow circulation of magma in chambers deep below. Each vibration adds another note to the ongoing symphony of planetary understanding. Yet even this vast network of sensitive ears is just part of a larger story. The vibrations they detect, the patterns they reveal, all unfold according to rhythms that operate on scales far grander than human experience. Your heart beats in a rhythm you have known since before you were born. Every 24 hours, your body temperature rises and falls with the sun. Every month, you notice changes that mirror the phases of the moon. These are the rhythms of human time, fast and immediate, tied to the brief span of a single life. But the Earth keeps time differently. Its rhythms are vast, patient, measured not in heartbeats but in millennia. To understand supervolcanoes, you must learn to think in this deeper time, where events that seem catastrophic to humans are simply part of ancient, predictable cycles. The Yellowstone supervolcano has erupted 3 times in the past 2 million years. The first eruption occurred 2.1 million years ago. The second happened 1.3 million years ago. The most recent took place 640,000 years ago. At first glance, these numbers might seem random, chaotic events scattered across time. But when scientists look more carefully, they see patterns. The time between the first and second eruptions was about 800,000 years. The time between the second and third was about 660,000 years. These intervals are not identical, but they are remarkably similar considering the vast scales involved. This regularity suggests that supervolcanic eruptions follow natural cycles. Like the seasons that return each year, like the tides that rise and fall twice daily, these volcanic giants operate according to rhythms built into the very structure of the Earth. The cycles begin deep in the planet's mantle, where hot rock rises from the core mantle boundary. This rising plume of molten material takes millions of years to reach the base of the crust. Once there, it spreads out like honey poured onto a table, creating what geologists call a hotspot. The hotspot melts the rock above it, creating a magma chamber that grows slowly over hundreds of thousands of years. As the chamber fills, pressure builds. Eventually, the pressure becomes too great for the overlying rock to contain. The chamber empties in a massive eruption, and the cycle begins again. But the Earth's clockwork operates on multiple levels simultaneously. While magma chambers fill and empty over hundreds of thousands of years, other cycles play out over millions of years. The continents drift across the surface, carried by the slow movement of tectonic plates. Ice ages come and go. Mountain ranges rise and erode away. These longer cycles interact with the volcanic cycles in complex ways. When ice sheets grow thick over volcanic regions, their weight can suppress eruptions. When the ice melts, the sudden release of pressure can trigger increased volcanic activity. Climate changes can alter the stress patterns in the Earth's crust, affecting when and where eruptions occur. Scientists have learned to read these overlapping rhythms by studying rocks that are millions of years old. They look for layers of volcanic ash in sedimentary formations. They analyze the magnetic properties of ancient lava flows. They examine the chemical composition of rocks that crystallize deep underground. Each piece of evidence adds another tick to the Earth's vast clock. Slowly, patiently, scientists are reconstructing the schedules that govern our planet's most powerful forces. They are learning to see order where previous generations saw only chaos. The orbital cycles of the Earth around the Sun also play a role in this deep time clockwork. Every 100,000 years, the Earth's orbit changes from nearly circular to slightly elliptical and back again. Every 41,000 years, the tilt of the Earth's axis shifts. Every 23,000 years, the timing of the seasons relative to the Earth's orbit changes. These astronomical cycles drive ice ages, which in turn affect volcanic activity. When ice sheets grow, they lock up vast amounts of water, lowering sea levels and changing the pressure on the Earth's crust. When ice sheets melt, the redistribution of weight across the planet can trigger earthquakes and volcanic eruptions. The beauty of deep time is how it reveals the Earth as a self-regulating system. When volcanic eruptions inject ash and gas into the atmosphere, they can trigger global cooling that leads to ice ages. When ice ages change sea levels and crustal pressures, they can affect the timing of future eruptions. Everything is connected across scales of time that dwarf human experience. This vast perspective brings a strange comfort. The same supervolcanic eruptions that seem terrifying when viewed from human timescales become natural, predictable events when viewed from the Earth's perspective. They are not random disasters, but part of the planet's way of regulating its internal temperature and pressure. Scientists find peace in understanding these deep rhythms. They know that supervolcanic eruptions will occur again, but they also know that such events follow patterns that can be studied and understood. The Earth is not chaotic or malicious. It is simply vast and patient, operating according to laws that remain constant across millions of years. The clockwork of deep time also reveals something profound about resilience. Life on Earth has survived multiple supervolcanic eruptions, ice ages, asteroid impacts, and other catastrophic events. Each time, ecosystems have recovered and evolved. The planet has healed itself and continued its slow dance through space. This resilience is built into the Earth's systems at every level. Volcanic eruptions that devastate local ecosystems also create new land and enrich soils with minerals. Ice ages that destroy existing habitats also create new ones as sea levels change. Even the most dramatic events become, over deep time, part of the process that keeps the planet alive and changing. Tonight, as your own biological clocks prepare your body for sleep, remember that you are part of this vast temporal symphony. Your brief lifespans are nested within longer cycles of family generations, which are nested within the rise and fall of civilizations, which are nested within the slow breathing of ice ages, which are nested within the even slower rhythms of supervolcanic cycles. Each level of this nested time operates according to its own logic and its own sense of urgency. What seems immediate and critical from one perspective becomes patient and predictable from another. The Earth's clockwork teaches us that some problems require not speed, but patience. Some understanding comes not from rushing, but from learning to think in deeper time. The regular rhythms of supervolcanic cycles also point toward something else, the possibility of prediction. If these systems follow patterns, then perhaps those patterns can be used to anticipate what comes next. Step outside before sunrise on a clear morning. Watch how darkness slowly gives way to light. First, the eastern horizon shows just a hint of pale gray. Then comes a band of deep blue. Gradually, colors appear: soft pink, gentle orange, warm gold. The sun does not suddenly appear. Dawn announces itself slowly, painting the sky in stages that unfold over nearly an hour. Supervolcanic eruptions announce themselves the same way. They do not happen suddenly, without warning. Like dawn breaking across the landscape, the signs of a coming eruption appear gradually, building in intensity over years or even decades. This slow build-up of warning signs is one of the most comforting discoveries that scientists have made about supervolcanoes. The Earth does not keep secrets about its most powerful forces. Instead, it broadcasts its intentions clearly to anyone who knows how to read the signals. The first hints appear decades before an eruption. Deep in the magma chamber, molten rock begins to move more actively. This increased activity creates small earthquakes that sensitive instruments can detect. At first, these earthquakes are so tiny that humans cannot feel them. But they appear in seismometer records as gentle reminders that something is stirring below. As more magma accumulates in the chamber, the earthquakes become more frequent. What started as one small tremor per week might increase to several per day. Scientists track these earthquake swarms like meteorologists track approaching storm systems. The patterns tell them whether activity is increasing or decreasing. The rising magma also begins to push upward against the rock above. This creates the ground deformation we explored in earlier chapters. The land starts to rise, slowly and steadily, like dough rising in a warm kitchen. Modern instruments can detect this uplift when it measures only millimeters, years before it becomes noticeable to the human eye. As the eruption approaches, hot gases begin escaping from the magma chamber in greater quantities. The chemistry of these gases changes as conditions underground become more active. Springs that were once cool become warm. Geysers that erupted regularly might change their timing. New hot spots appear where none existed before. Scientists monitor these changes using networks of instruments that work like an early warning system for volcanic activity. Temperature sensors track heat flow from the ground. Gas analyzers sample the air for volcanic gases. Satellite radar measures ground deformation with incredible precision. All of this information flows into computer models that help scientists understand what is happening underground. These models are like weather forecasting systems, but instead of predicting tomorrow's rain, they track changes that unfold over years and decades. The beauty of volcanic early warning systems is how they transform uncertainty into understanding. Instead of fearing the unknown, scientists can watch volcanic systems change and evolve. They can see patterns emerging long before they become dangerous. Historical records support this gradual pattern of volcanic awakening. Mount St. Helens, which erupted in 1980, showed clear warning signs for months before the eruption. Small earthquakes began in March. The mountain started swelling as magma pushed upward. Steam explosions occurred weeks before the main eruption. Even more dramatic examples come from other volcanic systems around the world. Before Mount Pinatubo erupted in the Philippines in 1991, scientists detected increasing earthquake activity, ground deformation, and gas emissions for months. This early warning allowed them to evacuate nearby communities, saving thousands of lives. Supervolcanoes show even longer warning periods than regular volcanoes. The Yellowstone system, for example, goes through cycles of uplift and subsidence that can last decades. Scientists have been monitoring these cycles since the 1970s, learning to distinguish between normal breathing patterns and signs of increasing activity. The current scientific consensus is that a supervolcanic eruption would announce itself clearly for years, possibly decades, before occurring. The magma chambers are so large that filling them with enough molten rock to trigger an eruption would create unmistakable signals in earthquake patterns, ground deformation, and gas emissions. This extended warning period gives humanity time to prepare and adapt. Unlike earthquakes, which can strike without warning, supervolcanic eruptions unfold slowly enough that scientists can track their progress and predict their timing with increasing accuracy. Modern communication systems ensure that early warning information reaches decision-makers quickly. When volcanic monitoring systems detect significant changes, automated alerts notify scientists around the world within minutes. International cooperation means that expertise and resources can be shared rapidly when needed. But perhaps the most reassuring aspect of volcanic early warning systems is how they reveal the Earth's fundamental predictability. Even the most powerful geological forces follow patterns that can be understood and anticipated. The planet is not mysterious or capricious. It operates according to physical laws that human intelligence can comprehend. The gradual nature of volcanic warnings also reflects something deeper about how the Earth works. Natural systems tend toward balance and stability. They resist sudden changes and prefer gradual transitions. When major changes do occur, they typically build up slowly, giving other parts of the system time to adjust. This pattern appears everywhere in nature. Rivers do not suddenly change course, they gradually carve new channels over time. Mountains do not appear overnight, they rise slowly as tectonic forces push them upward. Climate changes unfold over decades and centuries, not days and weeks. Supervolcanic eruptions follow this same pattern of gradual change. They are not random catastrophes, but natural events that announce themselves clearly to anyone paying attention. The Earth provides ample warning because its systems are designed to maintain stability whenever possible. Tonight, as you prepare for sleep, remember that scientists around the world are maintaining their patient watch over the sleeping giants. They are reading the subtle signals that flow continuously from deep underground. They are learning to distinguish between normal variation and meaningful change. The early warning systems work like faithful sentinels, watching for the first hints of dawn in a volcanic night. When that dawn eventually comes, it will not arrive suddenly or without notice. Like the sunrise you can watch any clear morning, it will announce itself gradually, painting the scientific instruments with clear, unmistakable signals that build over time. But these warning systems are more than just technical achievements. They represent humanity's relationship with the powerful forces that shape our planet. As you settle into your bed tonight, millions of people around the world are doing the same. In houses and apartments, in cities and countryside, people are ending their days and preparing for rest. Most of them live their entire lives without thinking about the sleeping giants that lie beneath their feet. But in laboratories and monitoring stations scattered across the globe, a small community of dedicated scientists remains awake. They are the watchers, the guardians who have chosen to spend their careers listening to the Earth's deepest whispers. While the world sleeps, they keep vigil over forces older than human memory. Their work is not dramatic or urgent in the way that movies might portray. There are no flashing alarms or desperate countdowns to midnight. Instead, there is patient observation, careful measurement, and the slow accumulation of understanding that builds over decades. In Yellowstone, a scientist checks the latest data from seismometers scattered across the park. The readouts show the gentle, steady heartbeat of the magma chamber below. A few small earthquakes, no larger than the vibrations caused by a passing truck. Some thermal variations at hot springs that fall well within normal ranges. All the vital signs of a system that is alive but peacefully sleeping. In Iceland, researchers analyze gas samples collected from geothermal areas. The chemical signatures tell familiar stories of deep heat and ancient rocks. The ratios of different gases match patterns observed for years, confirming that underground processes are following their normal cycles. In Indonesia, satellite data reveals the slow breathing of land above the Toba caldera. The ground rises and falls by millimeters each year, following patterns that scientists have learned to recognize as the natural rhythm of a resting supervolcano. This global network of monitoring represents one of humanity's greatest achievements, the transformation of fear into understanding. For most of human history, volcanic eruptions were mysterious, terrifying events that could only be explained through mythology and superstition. Today, they are natural phenomena that can be studied, measured, and predicted. The scientists who do this work are not motivated by fear, but by curiosity and care. They want to understand how the Earth works. They want to protect human communities from natural hazards. They want to ensure that future generations inherit a world where knowledge has replaced ignorance about the forces that shape our planet. Their vigilance creates a safety net that spans the entire globe. When unusual activity occurs at any monitored volcanic system, information flows instantly to researchers around the world. Expertise and resources can be shared rapidly. The global scientific community functions as a single, intelligent organism dedicated to understanding and safety. But perhaps most importantly, this scientific vigilance teaches us how to live in harmony with powerful natural forces. The Watchers have learned that supervolcanoes are not enemies to be feared, but natural systems to be respected and understood. They are part of the Earth's way of regulating its internal temperature and pressure. They create the landscapes we find beautiful and the soils that support our agriculture. The same magma chambers that could someday produce massive eruptions also power the geothermal systems that provide clean energy. The same thermal processes that scientists monitor also create the hot springs that offer healing and relaxation. The same deep forces that require careful watching also drive the plate tectonics that continually renew our planet's surface. Living in harmony with sleeping giants means accepting that we share the planet with forces much larger and older than ourselves. It means recognizing that our human timescales of days and years are nested within much longer cycles of geological time. It means finding comfort rather than fear in the Earth's vast patience and predictability. The scientists who watch over supervolcanoes model this harmony in their daily work. They approach these powerful systems with respect, not terror. They seek understanding, not conquest. They work to protect human communities while also appreciating the natural beauty and importance of volcanic processes. Their example teaches us that knowledge is humanity's greatest tool for living safely in a dynamic world. Understanding weather patterns helps us prepare for storms. Understanding ocean currents helps us navigate safely. Understanding volcanic systems helps us coexist peacefully with some of the Earth's most powerful forces. The monitoring networks also represent hope for future generations. The data being collected today will help scientists of tomorrow better understand how volcanic systems evolve over time. The techniques being developed now will enable more accurate predictions and better preparation for rare but significant events. Children growing up today will inherit a world where supervolcanoes are better understood than they have ever been in human history. They will have access to monitoring systems that can provide decades of advance warning before major eruptions. They will be part of a global civilization that has learned to work together in studying and preparing for natural hazards. This legacy of knowledge and cooperation is perhaps the most beautiful aspect of modern volcanology. Scientists from different countries, cultures, and backgrounds work together toward common goals. They share data freely. They collaborate on research projects. They support each other during volcanic crises. Their work creates a kind of planetary nervous system that helps humanity sense and respond to changes in the Earth's deep processes. Like neurons in a vast brain, monitoring stations gather information that flows to centers of analysis and decision-making. The result is a level of awareness about our planet that previous generations could never have imagined. Tonight, as you drift toward sleep, you can take comfort in knowing that this global network of watchers continues its patient vigil. Seismometers listen to the Earth's heartbeat. Satellites track the slow breathing of continents. Scientists analyze the chemical signatures of gases rising from the deep places. Their vigilance is a gift to all of humanity. It transforms the unknown into the known, the fearsome into the understood, the chaotic into the predictable. It allows us to live peacefully on a dynamic planet, knowing that we have learned to read the signs that matter. The sleeping giants rest on, following rhythms older than human civilization. And we rest peacefully too, wrapped in the protective embrace of human knowledge and dedication, knowing that understanding brings safety, and that wonder can replace fear when we learn to listen to the deep stories that our planet tells.